Hello and welcome to another discussion series in General Chemistry 2. For the past topics, our discussions focused primarily on pure substances, elements, covalent compounds, and ionic compounds. However, most of the matter with which we come into contact is a mixture. In this series, we will be focusing on solutions which are homogeneous mixtures of two or more substances. So we will be discussing the following: solubility, concentration, solution stoichiometry, and colligative properties. Recall that from General Chemistry 1 that a mixture has two defining characteristics. Its composition is variable and it retains some properties of its components. We focus here on the two common types of mixtures, which are solutions and colloids, whose main differences relate to particle size and number of phases. So a solution is a homogeneous mixture and exists as a single phase, wherein the particles in a solution are individual atoms, ions, or small molecules. While colloid is a heterogeneous mixture and exists as two or more phases which may be visibly distinct. The particles in a colloid are typically macromolecules or aggregations of small molecules. In a solution, a solute dissolves in a solvent to form a solution. Usually, the solvent is the most abundant component, but in some cases, the substances are miscible, which is soluble in each other in any proportion. So the physical state of the solvent usually determines the physical state of the solution. So solutions can be gaseous, liquid, or solid, but we focus mostly on liquid solutions because they are by far the most important. And when we say solubility, the solubility of a solute is the maximum amount that dissolves in a fixed quantity of solvent at a given temperature. Solubility is a quantitative term, but dilute and concentrated are qualitative, referring to the relative amounts of dissolved solute, which we will discuss in the slides to follow. A given solute may dissolve in one solvent and not another. That's why substances that exhibit similar types of intermolecular forces dissolve in each other, often expressed by saying like dissolves like. So when a solution forms, solute-to-solute attractions and solvent-to-solvent attractions are replaced by solute-to-solvent attraction. This can only occur if the forces within the solute and solvent are similar to the forces that replace them. Illustrated here are some of the intermolecular forces that we have discussed previously. So we have here the hydrogen bond, and then the dipole-dipole forces, and the dispersion forces. So here is the dissolving process of sodium chloride. So when sodium chloride crystals are dissolved in water, the polar water molecules exert attracting forces which weaken the ionic bonds. So the process of solution occurs, the ions of sodium and chloride become hydrated. Now, what determines if a compound dissolves in a particular solvent? Whether a compound is soluble in a given solvent depends on the strength of the interactions between the compound and the solvent. As a result, compounds are soluble in solvents to which they are strongly attracted. That is, compounds are soluble in solvents with similar intermolecular forces. That is why previously we have said that solubility is often summed up in three words, like dissolves like. So most ionic and polar covalent compounds are soluble in water, which is a polar solvent. So water-soluble compounds are ionic or are small polar molecules that can hydrogen bond with water solvent. For example, here, solid sodium chloride is held together by very strong electrostatic interactions of the oppositely charged ions. When it is mixed with water, the sodium ion and chloride ions are separated from each other and surrounded by polar water molecules. Each sodium ion is surrounded by water molecules arranged with their oxygen atoms in close proximity to the positive charge of the cation. while each chloride ion is surrounded by water molecules arranged with their hydrogen atoms in close proximity to the negative charge of the anion. Although ionic compounds are generally water-soluble, some are not. If the attraction between the ions in a crystalline solid is stronger than the forces of attraction between the ions in water, the ionic compounds does not dissolve. The identity of the cation and anion in the ionic compound determines its water solubility. So we have here two rules which can be used to predict water solubility, which are presented here. Let's say, for example, sodium carbonate is water soluble because it contains sodium cation according to rule number 1, but calcium carbonate is water insoluble because it contains none of the ions listed in rules 1 and 2. In dealing with the solubility of ionic compounds in this text, we will assume the compound to be water soluble unless specifically asked to consider the solubility rules just mentioned. We also have to remember that small neutral molecules with oxygen or nitrogen atoms that can hydrogen bond to water are also water soluble. While nonpolar compounds are soluble in nonpolar solvents, like what we have discussed before, like dissolves like. Now, as a result, octane, as illustrated here, is a component of gasoline that dissolves in the nonpolar solvent carbon tetrachloride or CCl4 as shown in this figure. Animal fat and vegetable oils, which are composed of largely nonpolar carbon and carbon bonds and carbon and hydrogen bonds, are soluble as well in carbon tetrachloride but are insoluble in polar solvent like water. These solubility properties explain why oil and water don't mix. Dissolving a solute in a solvent is a physical process that is accompanied by an energy change. Breaking up the particles of the solute requires energy, and forming new attractive forces between the solute and the solvent releases energy. We have here an example on health and medicine, particularly vitamins. So the difference between hydrophilic and hydrophobic substances has substantial consequences in biological systems that you discussed in general biology subjects. So vitamins can be classified as either fat-soluble or water-soluble. For fat-soluble vitamins such as vitamin A, they are nonpolar hydrophobic molecules and tend to be absorbed into fatty tissues and stored there. So these kind of vitamins are renewed usually once in a while, but unlike water-soluble vitamins like vitamin C, they are polar or hydrophilic molecules that circulate in the blood and intracellular fluids and are excreted from the body and must be replenished in daily diet. So in here is the illustration on where vitamins A and vitamin C are located. Again, vitamin A are fat-soluble vitamins. They are nonpolar. While vitamin C are water-soluble vitamins and they should be renewed in the diet daily. In terms of the types of solutions, we have three. So when an excess amount of solid is added to a solvent, particles leave the crystal which are surrounded by the solvent and move away. Some dissolved solute particles collide with undissolved solute and recrystallize, but as long as the rate of dissolving is greater than the rate of recrystallizing, the concentration rises. At a given temperature, when solid is dissolving at the same rate as dissolved particles are recrystallizing, the concentration remains constant and undissolved solute is in equilibrium with dissolved solute. So three terms express the extent of this solution process. The first one would be a saturated solution. So it contains the maximum amount of dissolved solute at a given temperature in the process of undissolved solute. Therefore, if you filter off the solution and add more solute, it doesn't dissolve. Now, for an unsaturated solution, it contains less than the equilibrium concentration of dissolved solute. If more solute is added, it will dissolve. The last one is a supersaturated solution, which contains more than the equilibrium concentration of solute. So it is unstable, and any disturbance will cause excess solute to crystallize immediately. You can often prepare a supersaturated solution if the solute is more soluble at higher temperature. While heating, it will dissolve more than the amount required for saturation at some lower temperature, and then slowly cool the solution, and if the excess solute remains dissolved, the solution is supersaturated. Let's examine now the effects of the different factors on solubility of solids and gases. The first one would be temperature. So for most ionic and molecular solids, solubility generally increases as temperature increases. By dissolving a solid in a solvent at high temperature and allowing it to cool slowly, a supersaturated solution can be made. And then a supersaturated solution contains more than the predicted maximum amount of a solute at a given temperature. In contrast, the solubility of a gas decreases with increasing temperature. So here's an example of most ionic solids which are more soluble at higher temperatures. We have here sodium nitrate, potassium chloride, sodium chloride, potassium chlorate, and cesium sulfate. Aside from temperature, we also have pressure. So pressure has a little effect on the solubility of liquids and solids because they are almost incompressible. But it has a major effect on the solubility of gases. We have here Henry's law, which describes the effect of pressure on gas solubility. So according to Henry's law, the solubility of a gas in a liquid is proportional to the partial pressure of the gas above the liquid. Therefore, the higher the pressure, the higher the solubility of a gas in a solvent. A practical demonstration of Henry's law occurs whenever we open a carbonated soft drink. Soft drinks contain dissolved carbon dioxide which are sealed under greater than 1 atmosphere of pressure. When a can is opened, the pressure above the liquid decreases to 1 atmosphere. So the solubility of the carbon dioxide in the soda decreases as well, and some of the dissolved carbon dioxide visces out of the solution. As we learned in gas laws discussion during General Chemistry 1, increasing gas solubility affects scuba divers because more nitrogen gas is dissolved in the blood under the higher pressures experienced underwater. Divers must ascend slowly to avoid forming bubbles of nitrogen gas in joints and small blood vessels. If a diver ascends slowly, the external pressure around the diver slowly decreases, and by Henry's law, the solubility of the gas in the diver's blood slowly decreases as well. As the pressure is increased, more gas particles collide with the liquid surface. So more gas particles dissolve until equilibrium is reestablished. And that is the end of our first part in this discussion series. Thank you for listening.